All right, let's get right into it. When you hear the word calculus, you probably think of this, impossible maze of formulas. But what if we looked at it a different way? What if it's actually a language? A language that was invented to describe a world that never ever stands still. So today, we're going to learn the basic grammar of that language, and it all revolves around one incredibly powerful idea: the derivative.
I mean, really think about that for a second. A car's speed is never perfectly constant, right? It's always changing. So how could you possibly know its exact speed at the precise instant it zips past a street sign? That's the puzzle. And it's the whole reason calculus was even invented in the first place. The derivative, well, that's the key that unlocks the answer. So, if we're going to learn this new language, we have to start at the very beginning with the alphabet. And in the language of change, the alphabet, the most fundamental building block, is the derivative. Now, the most important words on this slide are instantaneous rate of change. This is not about your average speed over a whole trip. This is about what's happening right now, in this exact moment. If you can picture a graph, the derivative is just the steepness, the slope of the curve at one single tiny point. That's the whole idea. Okay, let's make this feel real. Here we've got a function, d of t, that's just tracking a scooter's distance from home over time. Now, suppose someone tells you that the derivative at the 15-minute mark, or d prime of 15, is 650. What on earth does that actually mean in the real world? It means exactly this. We've just translated from calculus speak into plain English. At that exact moment, 15 minutes into the ride, the scooter is moving away from home at a very specific speed, 650 meters per minute. The derivative gives us that perfect instantaneous snapshot of what's happening. Let's try one more. So this time, P of t is modeling the air pressure inside a leaking tire. And let's say the math tells us that P prime of 3 equals -2. That little negative sign, that's the key to this whole thing. And this brings us to a super simple but crucial rule in our new language. If the derivative is positive, your number is going up. If the derivative is negative, like it is here, your number is going down. So at the 3-minute mark, the tire is actively losing pressure at a rate of 2 psi every minute. The sign literally tells you the direction of the change. So, knowing the rate of change at one specific point, that's really powerful. But what if we could use the derivative to tell the entire story of a function? To map out every single hill, every valley, every curve? We'll see how that works. So here's the big takeaway. Just by looking at the sign of the derivative, we know if our original function is going up or down. Wherever the derivative is positive, the graph is climbing. Wherever it's negative, the graph is falling. This is called the first derivative test, and it's our #1 tool for figuring out the basic shape of a function. But that's the next logical question, isn't it? I mean, a function can be going up, sure, but is it climbing like a gentle hill, or is it shooting up like a rocket? That bend in the curve tells a much deeper part of the story. And the first derivative alone, it just can't tell us that. Well, this bend has an official name. It's called concavity. And how do we measure it? Well, you're going to love this. We just do the same thing all over again. We take the derivative of the derivative. This is the second derivative, and its whole job is to tell us about the curvature of our function. And the rule is so simple. You can just see it. If the second derivative is positive, the graph is concave up, shaped like a U, kind of like a cup holding water. If the second derivative is negative, the graph is concave down, shaped like an upside-down U, spilling the water out. It's really that visual. And this all leads to a really fantastic shortcut. So you find a point where the graph is perfectly flat, the very top of a hill or the bottom of a valley. Then you just check the concavity right at that spot. If it's concave up, shaped like a cup, you must be at the bottom of a valley. That's a local minimum. If it's concave down, you're at the peak of a hill, a local maximum. And that's the second derivative test. Pretty clever, right? All right, let's shift gears and apply this language to where it feels most natural, the world of physics. The entire story of an object's motion is written from start to finish in the language of derivatives. Check this out, it's so elegant. If you have a function that tells you an object's position, we'll call it s of t. Its derivative is the velocity. That's how fast the position is changing. And what's the derivative of velocity? It's acceleration, how fast the velocity is changing. It's this beautiful, perfect chain of command. Okay, but here's a classic question that trips a lot of people up. You might think, oh, positive acceleration means speeding up. But it's actually a little more subtle than that.
The real answer comes from comparing the velocity and the acceleration.
And here's the secret. An object speeds up when its velocity and acceleration are working together, when they have the same sign. They could both be positive or they could both be negative. It's slowing down when they're working against each other with opposite signs. So get this. An object with negative velocity and negative acceleration is actually speeding up. It's just doing it in the negative direction.
Okay, so far we've looked at how one single thing changes. But let's be real. The world is way more connected than that. When one thing changes, it kicks off a chain reaction, causing other things to change too. And this brings us to our next huge idea, related rates.
Now, I know these problems can look really intimidating at first, but trust me, there's a reliable, step-by-step game plan. You always start by drawing a picture, just to see what's going on. Then you find a basic equation that connects your pieces, like a geometry formula. But the magic happens in step 4. You take the derivative of the entire equation with respect to time. That one move is what connects the speed of one part of your system to the speed of another.
The classic example is a ladder sliding down a wall. As you pull the bottom of the ladder away from the wall, the top has to slide down, right? Those two speeds aren't the same, but they are totally connected by the shape of that triangle. Related rates give us the exact mathematical tool to figure out precisely how fast the top is falling based on how fast the bottom is moving. You know, every language has its own special grammar rules for really tricky situations. Well, in calculus, we have a kind of secret weapon for solving limits that look absolutely impossible at first.
It's called L'Hopital's rule, and it's for those times you try to solve a limit and you get a nonsense answer like 0 divided by 0. When that happens, you don't give up. The rule says you can just take the derivative of the top function, the derivative of the bottom function, and then try the limit again. And amazingly, it often simplifies the whole thing and just gives you the answer. And here's a great piece of history. The rule is named after this French mathematician, L'Hopital, because he published it in the world's very first calculus textbook. But it turns out it was actually discovered by his teacher, Johann Bernoulli, who sold the rights to the discovery to him. It's a fun reminder that even in math, the story of big ideas is always a little complicated and human. So when you step back and look at it, the derivative really isn't just some abstract formula. It's a lens. It's a whole new way of seeing the world. It gives us the words and the grammar to describe motion, to understand shape, and to see how everything is connected as it changes. It really is the language of change. So the only question left is, what story are you going to tell with it?